This video is part of the lecture for multivariable calculus, and I'm going to talk about linear approximation. So let me start. Linear approximation of a function of just one variable, approximation of f of x. Okay, I'm gonna explain it to you in a graph. So I have x-axis, y-axis, and I have a function y equals to f of x at a point x naught. I have a line that is called tangent line, and I'm gonna say that the tangent line at a point x naught and f of x naught, which I'm gonna call it y naught, has the slope f prime of x naught, and I'm gonna write the equation of that as y minus y naught is equal to f prime of x naught x minus x naught. I'm gonna bring y naught, which is just a number, on the other side. I'm gonna get y equals to f prime of x naught x minus x naught plus y naught. I'm gonna call this part L of x. Since f prime of x naught is just a number, x naught and y naught are numbers, and x is the only variable, I have L of x. And let's say that I have a point A that is very close to the point x naught. Okay, then I'm looking for the value of the function at the point A. I'm looking for f of a. And as you see, when a is very close to x naught, the value of this function, the tangent line at the point A, is this. And as you see, these two are very close to each other, so I can approximate f of a with the value of the line at the point A. Okay, and I say that the value of the tangent line at A is L of a, and so when A is close to x naught, then I can say that the value of the function at A, which is basically this point, is approximately L of a. The value of the function, the value of the line, the tangent line at A. And so f of a is approximately, I'm gonna plug in a to my line in here. So I'm gonna write y naught, and y naught is basically f of x naught plus f prime of x naught. I'm gonna plug in a for x minus x naught. Okay, so this is called the linear approximation of the function y equals to f of x at the point x naught, and I can approximate the value of the function at the point A by plugging the point A into the tangent line. Okay, let's look at one example. So I'm gonna approximate square root of 1.1. Okay, how do I do that? I'm gonna let the function f of x to be square root of x. I'm gonna pick a point that is close to this number in here, so I'm gonna let x naught to be equal to 1. And so y naught, which is basically the value of the function at x naught, is square root of 1, which is basically 1. So I'm gonna write the tangent line at the point 1, 1. So slope of the tangent line is f prime of x, which is 1/2 x to the power of negative 1/2, and I'm gonna plug in x0 into that. I get 1/2. Okay, so I'm gonna write the equation of the tangent line, which is y minus the y value equals to f prime at a given point, x minus x0. Okay, so that's why L of x is equal to, I'm just gonna bring -1 on the other side. It would be 1/2 x minus 1 plus 1. Okay, now what is L of 1.1? It's 1/2 1.1 minus 1 plus 1. This is 0.1. Okay, so 0.1 divided by 2 plus 1, it would be 0.05 plus 1, which is 1.05. And that's why, since 1.1 is very close to the given 0.1, I'm going to say that the value of the function at 1.1, which is basically square root of 1.1, is approximately the linear approximation, or basically the tangent line at the point 1.1, which is 1.05. So this is approximately 1.05. Okay, that's how we use linear approximation to approximate a point for just one variable function. Let's look at linear approximation of a function of two variable. Okay, so for a function of two variable, I have a surface like this, x-axis, y-axis, and then z-axis, and I have a surface z equals to f of x and y. At any point, just assume that at this point, I have a tangent plane that is a plane that is tangent to the surface at the given point x0 and y0. Okay, equation of the tangent plane at the point x0, y0, and z0. Z0 is basically the value of the function at x0 and y0, is this. It has a normal vector. If you remember, the normal vector has this equation. It would be, the first coordinate would be partial derivative of the function with respect to x at a given point, x0 and y0. The second coordinate would be the partial derivative with respect to y at a given point, y0 actually. y0, and then the third coordinate is -1. So let me write equation of a plane that passing through this point with this normal line. So it would be f of x, so that's the tangent plane at the point x0, y0, x minus x0, plus the second component of the normal vector, x0, y0, add y minus y0, and then -1 at z minus z0 equals to 0. So I'm gonna write z equals to that. I'm gonna bring z on the other side, and I'm gonna left everything on the left hand side. So I'm gonna have fx at x0, y0, x minus x0, plus I'm gonna write this term in here, fy of x0, y0, y minus y0, and I have -1 times plus times negative z0, which would be just z0, and z0 is basically f of x0 and y0, so I'm gonna write this one. Very good. So basically I just brought z on the other side and I wrote equation of the tangent plane, and I'm gonna call this one L of x and y. This is basically the linear approximation okay, of this function at the point x naught and y naught. So I used the equation of the tangent plane to write the linear approximation. Okay, there are two facts that I would like to say. Fact one is that if fx and fy, they both are defined, they exist, and they're continuous in a neighborhood of x naught and y naught, then f of x and y is differentiable at the point x naught and y naught. Do you remember definition of differentiability in one variable calculus? It's the same thing, but we have partial derivatives now. We say that if the partial derivative with respect to x and with respect to y, they exist, they are defined, and they are continuous in the neighborhood of the given point, then the function is differentiable at that point. Okay, this is the fact one. And the fact two that I want to say, the fact two is that if the function of two variables f of x and y is differentiable, meaning that partial derivative with respect to x and y, they both exist and continuous in the neighborhood of x naught and y naught, then linear approximation this is the linear approximation at the point x naught y naught that we define, is a good approximation and the value of the function at the point a and b is approximately the linear approximation at the point a and b when, what is a and b actually? A and b is close to x naught and y naught. Okay, so how do we use these two facts? Let's look at one example. Approximate square root of 3.9 square plus 3.1 square. Okay, so I'm going to use linear approximation to approximate that. So I need to define my function first. So let f of x and y to be square root of x squared plus y squared. Okay, and I'm going to pick 2 points. Actually, I'm going to pick 1 point that is close to the given point. So let x naught to be 4, which is going to be very close to 3.9, and y naught to be 3, to be close to 3.1, and then z naught, which would be f of x naught and y naught, would be square root of 4 squared plus 3 squared. So this is 5. Okay, I can rewrite that at x squared plus y squared to the power of 1/2 to get the partial derivatives. I need to find the partial derivatives with respect to x. So it would be 1/2, I'm going to use chain rule, 1/2 x squared plus y squared to the power of negative 1/2 derivative of inside function with respect to x, which is 2x. So it would be x over square root of x squared plus y squared. Okay, and I'm going to plug in the point 4 and 3 into that. So I get 4 over square root of 4 squared plus 3 squared, which is 5. Okay, with the same idea, fy would be y over x squared plus y squared is just because the function is symmetric with respect to x and y. That's why I can replace y in here. And then I'm gonna say if y at the point 4 and 3 would be 3 over 5. Very good. Now let's look at the formula for linear approximation right there. Okay, and I'm gonna write L of x and y to be what? The partial derivative with respect to x, which is 4 over 5, x minus x naught, which is 4, plus partial derivative with respect to y at the point x naught, y naught, which would be 3 over 5, and then y minus y naught here would be 3, plus f of x naught, y naught, which would be 5. Very good. So that was the linear approximation. And so as you see, these partial derivatives, based on the fact that I explained in here, okay, so these two partial derivatives, they exist and they are continuous in the neighborhood of 4 and 3. It's just because this is the polynomial, this is a square root, both of them are defined, and they are continuous at the point in a neighborhood of 4, 3. Okay, we have a problem at 0, 0, but it's not very close to the point 4 and 3. And so the function is differentiable. Since the function is differentiable, then the linear approximation is a good approximation. That's why I can use linear approximation right now. And I'm gonna say that f of 3.9 and 3.1, which is what? Which is 3.9 squared plus 3.1 squared. It's approximately the linear approximation at this point. And then 3.1, okay? I'm gonna plug in 3.9 in here, so 4 over 5, 3.9 minus 4, plus 3 over 5. I'm gonna plug in 3.1 in here, 3.1 minus 3, and then plus 5. This is negative 0.1, this is 0.1, so together I get 5, I get negative 0.4 plus 0.3 plus 5, actually 25 now, because I use the common denominator. Do the math, you get 4.98. So I can say that this is 4.98. So let me show it to you, the graph of this function z equals to square root of x squared plus y squared. As you see, we have a cone like this in 3D, and then this is the equation of the tangent plane, 4 over 5, x minus 4 plus 3 over 5, y minus 3 plus 5. As you see, this is the tangent plane at the point 4 and 3. It's right there. And if I zoom in, you see that it's very close. The tangent plane is actually very, very close to the cone. That's why we use this as the linear approximation.